Hello, my name is Sebastian. I'm a PhD student at the Ruhr University Bochum, and I'm going to present our work with the title T0RTT Non-Interactive Immediate Fault Secret Single Pass Circuit Construction. This is joint work together with Robert Merget and Jörg Schwenk, Ruhr University Bochum, Kai Gellert, University of Wuppertal, and Tobias Sandürg, Paderborn University. Before I present our results, I would like to start with a short motivation and brief introduction to Tor. Providing the ability to browse the web anonymously has become a challenging task in the age of large-scale adversaries. One way to protect yourself against internet surveillance is to use the onion routing network, or short Tor. For this, Alice has to use a special onion proxy. The onion proxy builds so-called circuits in the onion routing network over a path of onion routers. To connect to web service hosted by Bob, Alice has to start the onion proxy, and the onion proxy establishes a session key with each onion router on the path. For this, a simple two-message protocol is used called NTOR. NTOR is basically a Diffie-Hellman key exchange. This has to be done for each onion router on the path, and every time a new session key is established, a new encryption layer is added. So after the circuit construction process, Alice can connect to the web service. And we see we have three different layers of encryption. The different layers of encryption ensure that each onion router on the path only knows its predecessor and successor. An attacker that observes or even controls one of the onion routers is therefore not able to link a starting point of the path to an endpoint of the path. And this property is called unlinkability and provides the anonymity in the Tor network. But as you can see, the circuit construction process is not really efficient. We need a lot of messages to establish all these keys. We need n times n plus 1 messages, which means for a path of standard length 3, we need 12 messages. And let's say the latency between the hops is 100 milliseconds, then the duration of the whole circuit construction process is 1200 milliseconds. But the interaction between Alice and the different onion routers provides a really important property, namely fault secrecy. What does fault secrecy mean? Let's say an onion router establishes different sessions with different clients over some time. And for this, the onion router uses a long-term key pair. And at some point, an attacker compromises the onion router and gets the secret key. Then fault secrecy guarantees that the attacker cannot use the secret key to gain any information about already established session keys. All modern key exchange protocols try to provide this property because it prevents, for example, that large-scale adversaries store a massive amount of encrypted communication data to decrypt it at a later point in time when the attacker gets access to the secret key. In NTOR, this is achieved using a Diffie-Hellman key exchange. So our research question was, can we make this circuit construction process more efficient? Can we get rid of this massive message overhead, but still provide unlinkability and fault secrecy? And our basic approach for this is to use zero round-trip time protocols. A zero round-trip time protocol, or short T0RTT protocol, give Alice the ability to send encrypted payload within the first message to the onion router. And a trivial approach to achieve the T0RTT property is to use public key encryption. Here, Alice can use the public key of the onion router to encrypt a randomly chosen symmetric key. Then she sends the encrypted key to the onion router, and additionally, she can send encrypted zero round-trip time data. The onion router can use the secret key to decrypt the session key and then decrypt the zero round-trip time data. Interestingly, this approach was already used in 1996 by Goldschlag et al. To build a single-pass circuit construction protocol. But this approach has two major weaknesses. First of all, there's absolutely no fault secrecy for the symmetric key. Any attacker that gets access to the secret key of the onion router can use the secret key to decrypt all session keys that has been encrypted under the corresponding public key. Another weakness is the missing replay protection. An attacker can easily replay this encrypted symmetric key and the zero round trip time data to the onion router. And in the worst case, an onion router would reestablish a circuit. And the attacker can use these information to gain any information about starting points and endpoints and break the unlinkability property. So it seems that the interaction between Alice and the onion router is fundamental basis to achieve fault secrecy. But in 2015, Green and Myers published a new cryptographic primitive called puncturable encryption. And puncturable encryption can be used in non-interactive settings to achieve fault secrecy. And non-interactive settings are settings in which an initiator sends only one message to a responder to establish a session key. And these settings are, for example, zero round trip time key exchange or email security. So let me give you an intuition on how zero round trip time with puncturable encryption works. Similar to public key encryption, an onion router has a secret and a public key pair. The public key is static and can be used to encrypt a randomly chosen session key. Then Alice sends the ciphertext to the onion router, and the onion router decrypts the session key. Then the onion router modifies its secret key. The secret key is non-static, and this process is called puncturing. The puncturing algorithm gets as input the secret key, the current secret key, and the ciphertext, and we get a new secret key. This new secret key can now be used to decrypt all ciphertexts except the ciphertext we have used to puncture the secret key. And this process can be done over and over again every time a new ciphertext is received. So we achieve immediately fault secrecy after puncturing the secret key. Additionally, we get replay protection. An attacker that replays an old ciphertext is not successful because an onion router is not able anymore to decrypt the ciphertext. And we can use these results in Tor to build a single pass circuit construction protocol. And we call this protocol T0RTT, which is a combination of Tor plus zero round trip time. In T0RTT, each onion router has a secret and a public key pair of a puncturable encryption scheme. And the onion routers can compute these keys by themselves. Alice can use the public keys to encrypt 3 different symmetric keys. Then she sends one onion message to the first onion router on the path. And this onion message contains all ciphertexts. And we call this onion message because ciphertext 2 and 3 are already encrypted in different layers of encryption. Then the first onion router decrypts the first symmetric key, removes one layer of encryption, and sends ciphertext 2 and 3 to the second router on the path. The second router on the path again uses secret key to get the symmetric key and sends the last ciphertext to the last router on the path. And we see after 3 messages, all session keys are established. Now, to confirm the success of the circuit construction, the last router sends an encrypted confirmation message back to Alice, and each onion router adds one layer of encryption. We call this single pass because we need only one message sent by Alice to establish all the session keys and to build the circuit. To achieve fault secrecy, each onion router on the path puncture its secret key immediately after receiving a ciphertext, and a new secret key replaces the old secret key. And this has to be done for each onion router on the path. So what we get is the first single path circuit construction protocol, which achieves forward secrecy immediately after the circuit construction. And our protocol needs only 2 times n messages to achieve this. T0RTT is fully generic, which means we can use any CCA secure puncturable encryption scheme. And let's say the puncturable encryption scheme is super efficient, then T0RTT is super efficient. If the encryption scheme provides post-quantum security, then T0RTT is post-quantum secure. We analyzed our protocol using the Bloom filter puncturable encryption scheme by Della et al. And this puncturable encryption scheme offers fast puncturing procedures, small ciphertext, and small public keys. So everything we need for Tor. For a security level of 128-bit, we see that the computation times at the client and the onion routers are a bit higher, but getting rid of all these messages, we see that the overall construction time is 500 milliseconds faster than in the current end-to-end handshake, assuming that the latency between the hops is 100 milliseconds. But our approach has also a few drawbacks, and we think all these drawbacks are manageable. First of all, current punctual encryption schemes suffer under large secret keys. This is due to the puncturing property and is unavoidable. So for a lifetime of 28 days for a public key and 1 million requests per day for the onion router, the onion router has to store a secret key of 20 gigabyte size. So onion routers need bigger storage. Another problem is that T0RTT has no post-compromise security. In the current end-to-end handshake, if an attacker gets access to the secret key of the onion router, the attacker has to act as an active man in the middle to read and alter messages. In T0RTT, the attacker can do this passively for the rest lifetime of the public key. And thanks to our fantastic reviewers, we discovered another problem regarding the unlinkability property. In our security model, unlinkability requires that the puncturable encryption scheme has zero connectedness error, which means if we encrypt a symmetric key correctly and the secret key was not punctured for this ciphertext, then the decryption should always be successful. Unfortunately, the Bloom filter encryption scheme does not provide perfect correctness. In fact, it has a non-negligible correctness error, and this can lead to an attack when passive attacker can break the unlinkability property. But again, we can solve this problem, and for this, let's have a closer look on how we define unlinkability. In our security model, we consider a network in which multiple users build circuits over a path of 3 onion routers. And here, Alice and Bob use the same middle node. Unlinkability is given if an attacker cannot link outgoing messages of the middle node to the incoming messages. So the attacker is not able to say which user has sent the onion message originally. And now let's say we have a puncturable encryption scheme with non-negligible correctness error. And an attacker can see that an onion will fail at the middle node. And here the onion was sent by Alice. And the attacker can see that a certain circuit is not built. Then it's easy for an observer to link the last onion message to Bob. But we solve this problem by using a technique we call dummy onions. If an onion message would fail at the decryption process, the onion router has to output a dummy onion. This dummy onion should be indistinguishable from a message that would have been sent if the decryption process was successful. So now the attacker may see that the onion message sent by Alice will fail at the middle node, but the attacker is not able to distinguish the real onion from the dummy onion, and the attacker cannot link the last onion router to Bob, which means we have achieved unlinkability again. So all in all, we have shown that it is possible to build single-pass circuit construction protocols with immediate fault secrecy. Yes, there are a few problems we are working on, and we are currently working on an implementation to use in a real Tor environment. So if you have any questions or if you are interested in working with us, feel free to contact me. Thank you very much for your attention.